Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on structure of metamorphic rocks. Today, I will proceed under the following heads: introduction and common metamorphic structures. Hope it will be useful for you. Try to be regular in course. The names of most metamorphic rocks are based primarily on structure and mineralogical characteristic. The most striking feature which stamps a rock as metamorphic is its fabric or structure and texture, which is the foliation and lineation. Therefore, the widely used rock names are schist or gneiss. The group name is also modified by a term which indicates a conspicuous structure or for example, gneiss. The group name can be further modified by the name of an index mineral placed as a prefix to the group name. For example, garnet schist. The name of the index mineral or key mineral indicates a specific condition of metamorphism. If a rock is almost monomineralic, it may be named after the dominant minerals. For example, quartzite dominated by quartz, marble by calcite or dolomite, serpentine almost entirely made up of serpentine, and like in other nomenclature, some terms invoke genetic assumption and employ such prefix such as para and ortho, which are used respectively for sedimentary and igneous protolith. Orthogneiss or para-amphibolites and orthoamphibolites are the terms used in this sense. Metamorphic rocks are derived from transformation or solid state recrystallization of existing igneous, sedimentary and metamorphic rocks due to change in physical and chemical condition, primarily temperature, pressure and introduction of chemically active fluid and gases. Metamorphic rocks preserve in their minerals a long history of the metamorphic process that affect them, while the mineral assemblages preserve information about pressure, temperature and fluid composition. Their texture mutual grain relationship give information about stress, strain, temperature history of the rock. Many texture in metamorphic rocks result from growth of new minerals or recrystallization of pre-existing minerals of parent rocks that was subjected to deformation stress at increase of temperature. The structure are more appropriately called dynamothermal textures because they occur in any situation where deformation and heat are combined. Such situations range from deep shear zone to strained contact areoles, but the majority of dynamothermal rocks are found in ancient orogenic belts. So we will concentrate on this setting. Orogenic belts are complex tectonic environments where plate convergence produce a number of deformational and thermal patterns. We can envision an orogeny as a long-term mountain building process, such as alpine orogeny and Himalayan orogeny. Orogenesis are not continuous, however, and an orogeny may comprise more than one tectonic event. Tectonic events in turn may be consist of more than one deformational phase. A deformation phase, according to Presser and Throw in 1996, a distinct period of active deformation with a specific style and orientation. Deformation phase may be separated by period of reduced or absent of deformation, during which the orientation of the stress field may change. A tectonite, a deformation rock with a texture, and record the deformation by developing a preferred mineral orientation of the same sort. Foliation, a general term for any planar textural elements in a rock, whereas lineation similarly applies to the linear elements. Foliation and lineation can be subdivided into primary pre-deformational ones such as bedding and secondary deformational one. Mineral may be oriented by either deformational preferred orientation DPO or lattice preferred orientation LPO, or both. Although they are treated separately, there is probably a complete natural gradation from pure foliation through combined foliation and lineation to pure lineation. Foliation, a number of features can be defined. A secondary foliation includes platy minerals, linear minerals, layers, fracture, and flattened elements. Metamorphic foliation are divided into cleavage, fine penetrative foliation, cystosity, coarse penetrative foliation, and gneiss structure, poorly developed coarse foliation, or segregated layers. Foliation is defined as a pervasive planar structure that results from the nearly parallel alignment of the seed silicate minerals and or compositional and mineralogical layers in the rock. Most foliation is caused by the preferred orientation of phyllosilicate like clay minerals, micas, and chlorite. Preferred orientation develop as a result of non-hydrostatic or differential stress acting on the rock, also called diabatic stress. We here review the differences between hydrostatic and differential stress. Type of foliations: a compositional layering, second, preferred orientation of platy minerals, third, shape of the deformed grains, fourth, grain size variation, fifth, preferred orientation of platy minerals in a matrix without preferred orientation, sixth, preferred orientation of lenticular minerals aggregate, preferred orientation of fractures, combination of the above. The first step in characterizing a cleavage is to decide whether the foliation elements are continuous or spaced. In a continuous foliation, the aligned minerals define a foliation that does not vary across the area of thin section. In a spaced foliation, the fabric of the rock is separated into unfoliated microlithons separated by cleavage domain, fracture or concentration of platy minerals. Fine-grained continuous cleavage may also be called slaty cleavage because its typified state phyllites have a slightly coarser continuous cleavage, and when individual aligned crystals become large enough to see with the added I, the foliation is called a cystosity. Spaced foliation are further subdivided and described on the basis of the spacing and shape of the cleavage domain, the presence of the granulation, the spatial relation between the domains, and the whether the domains grade into microlithons or not. A granulation cleavage is actually two cleavages. The first cleavage may be a slaty cleavage or cystosity that becomes microfolded. The folds may be symmetrical or asymmetrical. Quartz grains commonly dissolve by pressure solution from the folds limbs or just the steeper limb of asymmetrical folds, either to precipitate in the hinge areas or transport it further away. If the metamorphic temperature is high enough, new micas may also grow. Compositional layering is a common type of foliation that can be either primary or secondary. Primary layering, such as bedding, cumulate layering, or igneous flow feature, is inherited from the pre-metamorphic rocks. We shall discuss secondary layering in more detail. Foliation generally occur when theta 1 more than theta 2 and theta 3, and lineation generally occur when theta 2 is more than theta 3 or when shear seams out an object, as shown in figure. There are also several types of lineation. They usually result from the elongation of minerals or mineral aggregation, stretching lineation, stretch pebbles in deformed conglomerates are a common example. Lineation may also result from parallel growth of elongated minerals, fold axis, or intersecting planar elements, cleavage and beddings, or two cleavages. Note in figure that under some circumstances, planar mineral can create a linear fabric, just as linear mineral can create a planar fabric. Lineation is a one-dimensional structure. Primary lineation found in both igneous and sedimentary rocks. The long axis of prismatic minerals are oriented parallel to one another. This is particularly true of a mineral such as hornblende feldspar. Secondary lineation, sometimes secondary lineation are superimposed on rock after they were originally deposited. Secondary lineations may imposed on rocks more than once, so that several differential oriented minerals lineation may be present on rock. It may be formed by the fluidity of the material because the rock under high pressure and temperature behave plastically and may occur without the foliation. Lineation due to rolling and rotation. Minor folds give rise to lineation due to rolling and rotation of drags. Slickenite and groups, it is also produced by making of fraction of one mass over others. For example, during faulting, stretching pebbles in a deformed conglomerate are a common example. Lineation may also result from parallel growth of elongated minerals, fold axis, or intersecting planar elements, cleavage and beddings, or two cleavages. The mineral behave as fairly rigid objects, although some minerals may deform internally by cataclasis during rotation. This mechanism occurs in low temperature area such as shallow shear zones and low temperature regional metamorphic. Crystal plastic deformation and recrystallization may also result in elongated minerals during shear or flattening. Flattening causes the foliation to be elongated normally, which parallels the shortest axis of the strain ellipsoid. If the initial stage is already foliated, flattening will be enhanced the foliation in its original orientation, and shear will reorientate. The reorientation of a foliation by folding or shearing is called transposition. Continuous cystosity development by dynamic crystallization of biotite, muscovite and quartz. A plain polarized light width of field 1 millimeter. B. Another samples with cross polars width of field 2 millimeter, although there is a definite foliation in both samples. The minerals are entirely strain free. Precious solution and solution transfer can produce elongated minerals shapes or enhance other foliation by dissolving minerals from high pressure areas. Loss of quartz from the limbs of folds make the mica foliation such more evident, as does removing carbonates or quartz to leave an insoluble residue that define a cleavage domain. Solution is much more effective in the presence of a fluid. Gneiss structure and layers gneiss structure is either a secondary layering in a metamorphic rocks or a poorly developed schistosity in which a platy mineral are dispersed. Gneiss structure can range from strongly planar to strongly linear. Fabric elements can range from nearly continuous layer to discrete lanceolate shape. Several metamorphic rocks types exhibit layering or lances on the centimeter to several millimeter scale, and in gneissic it is practically characteristic. Such layer in fine grained low grade rocks is generally relict bedding or igneous layering. Other textures and structural elements may be developed in deformed rocks, and minerals are folds and kink bands. Budinas in a process in which elements such as dikes or elongated minerals that are less ductile than other surroundings stretch and separate into tables or saucer shaped called budins, French or sausages, as the surrounding deform by ductile flow. Kink bands, deformational bands and twist within the same minerals as a result of their deformation. Kink bands develop in the pre-tectonic minerals. Minor folds are developed in some rock such as the schist due to the deformation. Slate, a very fine grained rocks characterized by slaty cleavage. In the field, a slate can be distinguished from the shell by the absence of earthy smell when the moist it with or breathe. It develop from cell and tend to break cliffs into thin flat sheet. Slate is the lowest grade metamorphic rocks that form from a cell parent rocks. Slate is made up of microscopic mica minerals, usually muscovite. These are flat minerals that are aligned parallel to each other. This orientation of the crystal causes slate to break easily in one direction. This probably is called slaty cleavage. This property is called slaty cleavage. Cell is made up of clay minerals, and most clay is not very stable under high pressure and temperature. As cell begins to metamorphose, heat and pressure cause the clay minerals to slowly crystallize into flat mica flakes. Slate breaks in a preferred orientation because the mica crystal that flat and tend to break along a flat direction during metamorphism. The mica grows with their flat dimension orientation at right angles to the maximum pressure. This process line all micas up and gives slate its characteristic cleavage direction. Slaty cleavage is one example of the metamorphic texture called foliation, which means layering. The color of slate depends on the chemical composition of its parent cell or mudstone. Red slates are rich in hematite and iron oxide. Green slates contain a significant amount of chloride. Purple slates are constrained by magnesium oxide, and black cell contain carbon-rich organic material. Slate structure is also known as slaty cleavage, formed during the early stage of low-grade metamorphism due to lithostatic stress. The structure is due to the parallel orientation of flaky minerals. Phyllite, a fine-grained and very finely schistose rocks that develops from slate, the foliation S surface of which is due to the presence of ceriate. The cleavage surface so lustrous seen due to coarsening of mica, cerussite, muscovite and chlorite. The schistosity may be accentuated by thin segregation quartz-rich bands, which may alternate with micaceous band. Phyllite is a low-grade metamorphic rocks consisting mostly of fine-grained micas, but the mica crystals are large than those in slate and are large enough to be just barely visible to the naked eye. Phyllite typically developed from slate at temperature around 300 degrees centigrade. Other common minerals found in phyllite beside muscovite include chlorite, green, graphite dark gray or silvery, and sometimes garnets red or brown. They characteristic wavy, layered, glittering textures of phyllite is another example of foliation in metamorphic rocks. Schist, a strongly foliated, commonly lineated rocks which can be easily split up into plates of few millimeter thick. The schists are usually medium to dark colored and consist of lamellar minerals like micas, chlorite, talc, or prismatic minerals like amphiboles and sillimanite. If schist contains more quartz, relative to the sum of the phyllosilicates, which collectively are more than 50%, the rock is called quartz mica schist. Low modal amount of plagioclase, less than 10%, in schist distinguish them from gneisses. Schist is a medium-grained metamorphic rocks that can come from a variety of parent rocks, although the most common schists are from cell parents. This means that they come through a transition from cell to slate to phyllite to schist. Schist is characterized by an abundance of coarse mica minerals grains such as muscovite, biotite, and chlorite. The mica grains are large enough to be seen without magnification. Usually they can be flacked off with a fingernails. Schist display schistose texture, which is similar to phylitic texture, except that the minerals grains are coarse enough to be seen with the naked eye. Schist typically show little or no segregation of mineral into discrete bands or layers. Other metamorphic minerals, typically garnets, are commonly found sprinkled throughout the schist, formed due to the preferred orientation of linear minerals grain. For example, platy and flaky minerals due to recrystallization during regional metamorphism. Greenstone or green schist. Green colored low-grade metamorphic rocks dominated by the presence of chlorite, actinolites, and epidote minerals that may show schistose texture or non-schistose texture. To qualify the rocks as green schist or greenstone. This rock form mainly from metamorphic of a basaltic igneous parent rocks and is marked by the presence of chlorite, mica, which give green schist its characteristic green color. Blue schist, a metamorphosed mafic rocks containing large quantity of glaucophene blue amphiboles and has a pronounced schistosity. Gneiss, medium to coarse grained foliated metamorphic rocks marked by bands of segregate minerals, usually alternating light and dark colored minerals, known as gneissose structure. Gneiss is a high-grade metamorphic rocks only formed deep in the crust beneath active mountain chain such as volcanic arcs at subduction zone. Its prime distinguishing feature is gneissic texture formed by segregation of minerals into distinct and commonly colorful bands. It is split parallel to S surface, generally along micas or hornblende layers into plates or blocks of few centimeters. The term is almost exclusively used for rocks containing abundant feldspar and quartz. Unlike schist, the gneissic contain bands that are dissimilar in both texture and mineral composition. A field-based classification is on the basis of alkali feldspar or plagioclase feldspar. For example, 2 mica plagioclase gneiss or muscovite biotite alkali feldspar gneiss. The prefix ortho or para suggests its derivation from igneous or sedimentary parentage. As temperature approaches 500 to 700 degrees centigrade, a very hot but below the typical melting temperature of both rocks, the mineral is schist recrystallize and segregate into layers dominated by one mineral type. The extreme of heat and pressure destabilize the more felsic minerals, breaking them into ions that readily migrate within the rocks and recrystallize in distinct light-colored single mineral layers containing larger grains of more stable felsic mineral such as quartz or feldspar. Meanwhile, ions phased from other minerals such as biotite, amphiboles and pyroxene form layer of dark minerals. This process of mineral segregation is known as metamorphic differentiation. The distinct layering of dark and light minerals is referred to as gneissic banding, a striking form of foliated layered texture. When looking at layered rocks in lab or in the field, be certain not to mistake gneissic banding or layering in sedimentary rocks. These are two very different processes and textures. The two main differences are that sedimentary rocks layers are rarely segregated into separate minerals for each band, a characteristic of gneisses, and that the texture of sedimentary rocks is typically one of individual grains with certain in the space, not the interlocking crystalline texture of gneissic bands. Organ gneiss contain abundant porphyroblast, porphyroclast enveloped by the foliation to give the appearance of ice organ in German. Gaolites, a granoblastic rocks that is rich in quartz and feldspar and almost devoid of hydrous mineral, lenticular or tabular compositional layering may be present. Gaolites are equivalent of acid plutonic rocks, but those containing quartz, perthite, potash feldspar and hypersthene are preferred to as a charnokites. Granulose structures. Granulose structure is produced due to predominance of equidimensional minerals. Flaky minerals are absent or in less amount, so no foliation in rocks. A structure also known as saccharoidals. Cataclastic texture. Cataclastic structures formed under stress and in absence of high temperature. Rocks are subjected to shearing and fragmentation. Structures are formed due to cataclasis, therefore, as a whole called as cataclastic structure, that is myelonites and foliated breccia. A molecular structure is exhibited in argillaceous rock under contact metamorphism. Resistant minerals like cordierite, andalusite, biotite develop a spotted appearance. Horn felsic structure. Horn felsic structure is characteristic of contact metamorphism. Horn fels is a dark, compact, fine-grained rocks and iron foliated. This structure is formed due to predominance of equidimensional minerals. Amphibolite, a dark-colored rock composed primarily of hornblende and plagioclase, usually with quartz and epidote. Foliation due to alignment of amphiboles prism is less conspicuous than in schist. The qualification ortho and para suggest derivation from igneous or sedimentary rocks. Eclogites, a dense but rare rock of basaltic composition whose recrystallization at very high pressure and temperature give rise to an assemblage omphacite, solid solution of diopside and jadeite mainly, and high magnesium rich garnet with no plagioclase. Common accessory minerals are quartz, kyanite, amphiboles, geosite and rutile. Granophyls. Granophyls are non-schistose rocks characterized by isotropic granoblastic texture, mean grain size more than 0.1 millimeter. If less than 0.1 millimeter, the metamorphic rocks called hornfels. Marble, a crystallized carbonate rock composed of calcite or less commonly of dolomite. Serpentine, a green, black or reddish rock composed predominantly of serpentine, antigorite, chrysolite and chrysolite. It is formed by hydration of igneous or metamorphic petrotite, olivine-rich ultramafic rocks. Soapstone, magnesium rocks, a petrotite dolomitic limestone composed of talc with minor carbonates, chlorite and tremolite. Like serpentine, the soapstone are also formed by metasomatic alteration of the protolith. Skarn, a granoblastic rock that is rich in calcium silicate minerals such as gracilorite, andradite, epidote, dapsite, vesuvinite and wollastonite. The small amount of carbonate distinguishes skarn from marble. Skarn formed by SiO2 metasomatism at contact of limestone and igneous intrusive bodies, usually of granite composition. Skarn contains trace element of economic importance, molybdenum and tungsten. Quartzite, a monomineral rock composed predominantly of quartz and so granoblastic texture. Impurities in original protolith sandstone may form aluminous or ferromagnesium minerals. Dear student, today in this lecture we have discussed about the structure of metamorphic rocks. In this topic, I have covered the following heads: introduction and structure of metamorphic rocks. Study of metamorphic rocks are very important part of metamorphic petrology, as these can be useful to determine the deformational event as well as the regional or global history. These structures and textures should be properly identified and correlated with the deformation or for identification of protolith. Precautions must be taken during recognition of shear sense indicator. For further studies, please read the textbooks, references and links given in the text. Thank you very much.